Yeah, looks like we are live. I just now confirmed. Maybe you can refresh and then check. And please confirm me so that we can start the session.
Now it is working.
All right. Okay. So getting back to the first set of activity questions, the first question, we are given a set and A is a subset of which of the following is what we have to tell. So the first one, it's a set of integers, all right, whereas we have fractional values in our set, so A can't be a subset of the first option. The next one uh, we have an interval where -5 and 5 are not included, right? It's an interval where -5 and 5 would not be included, whereas in the given set we have -5 and 5 present. So second would be an incorrect option. The third one is a 6-dimensional space where each element belongs to real value. All right. So this should be indeed a tuple, a set of tuples, each having 6 values. That's how it is a 6-dimensional space. So that should be a tuple, whereas this is a set. So clearly this is not the right option. The last one is the set of real numbers, which could be positive or negative, or it could be fractional. So this should be the correct answer. A is a subset of the real space. Okay. The next one, which of the following correctly represents this term? Now, so what is RD? I hope this is clear to you. So when we talk about, let's say, when we talk about R3, we mean all those points which have 3 values. So we how do we represent the points? By a tuple. So each tuple should have 3 values. So let's say X, Y, and Z, 3 components should be there, and they all should belong to real space. Let's say 0.5, 0.3, let's say -2. It could be any value in the real space. Now, getting back, when we talk about A comma B, it's a closed interval, A comma B, and D-dimensional, that is. So this R is replaced by A comma B, and that is D-dimensional, which means, so here, if you compare with the R3, each tuple had 3 entries. Now each tuple should have D entries, right? And what should be the values of each of the element in this tuple? That was given by this R. Each of these values could belong to the real space. Now A comma B, now this R is replaced by A comma B and the closed interval, which means A and B are included, and any value between A and B. So this should be any value between A and B. This should be any value between A and B. It should be any value between A and B, and there should be D such values. This is how we interpret this particular term. Okay. Now let's see which of the following terms are equivalent to this thing. Okay. Now, if you check the last option, X belongs to RD, where Xi belongs to any value between A and B. Okay. Now X belongs to RD, which means we would have tuples, D-dimensional tuples. Okay. And each individual elements should be between A and B with a closed interval. Okay. And I goes from 1 to D. This is precisely what we just now mentioned here. Okay. Each individual element should be falling between A and B, with A and B inclusive, and there should be D such elements. So that's what the last option tells. So this should be the correct one. Checking the other options, the third option, if you see here, X belongs to RD, that is fine. Xi belongs to the set A comma B, which means the individual elements should be either A or B. That's all. So that's what we mean by the set, right? Rest is fine, but this is the only problem. Second option, if you see, there should be X1, X2, XD up to D elements, that is fine. And Xi belongs to R, okay, which is incorrect. Each Xi should belong to any element between A and B. So that's the wrong thing here. And looking at the first option, A comma B should be the elements of the set which is incorrect. So only the last option would be correct one. Okay.
Can I
The
ask a
first
question?
ma'am, the first question.
Yeah. First one, this one.
Yeah, why the option 3 is not correct?
3. What is, okay. Firstly, it's a set and there should be a tuple. See, this is a set, right?
Yes.
And any element which is a subset of R6 should be a tuple. Correct?
Each element will have six dimensions.
Yes. So, yeah. So if you talk about R3, let's say, this should be an element of R3. This should be an element in R3, right? The three components should be there. Similarly, if you talk about R6, there should be 6 values, and this should be a tuple, and this is 1 point in R6. Okay, this whole is 1 point in R6. So let's say you talk about a 2D space. How many values do you need to mention to represent a point?
2 points.
2 points, correct? So x1 and y1, let's say. This is how you represent 1 point. So if it is an R6, a 6-dimensional space, you need 6 such values, correct? That is one element in your R6. Now, if you want to have a subset of R6, then this subset where each element is of this type, okay, that would be the correct subset. Did you get it?
Correct. There is only one element is mentioned.
That also, and this is only, yeah. So, okay, this is a set, that is fine. There is only one element. Yeah, that's what I think you meant also. One element. Whereas it should be an element having, it should be a tuple having 6 values. Okay?
Yeah.
Regarding question number 2.
Yeah.
So last option, I should be starting 1 to D. So
Yeah.
I had confusion. So because it's already X belongs to RD. So, and I also belongs to 1 to D.
So so what is I here? Is that clear to you?
I is XI means how many?
So your
No,
X
I'm confused there.
X1, X2, X3, it's D, right? So up to D. So I goes from 1 to D. It's like that. Okay. So what are you saying here?
So X belongs to RD. That itself says that X
Yes,
will be like X1, X2 up
correct.
to XD.
Correct. So there is a redundancy of information here. You're right. X belongs to RD itself says that the individual elements will have, as in the X should have D values, correct? So this is an extra information.
Right.
So you're right there. X belongs to RD indeed conveys the same point. Okay. Yeah, that should be fine as well. So if you're not given this part, so it should be correct as well.
Yes. Yeah. Thank you, ma'am.
Yeah. Third question. If the vectors U and V belong to a vector space V, so I hope you studied vector spaces in Maths 2 course extensively. So we are just having a very brief over here. So when two vectors U and V belong to a vector space, then what happens? Can somebody tell?
Any linear combination is also in the vector space.
Yeah, their linear combination also belongs to the same vector space. And what could be the linear combination? If you add any two vectors?
Alpha U plus beta V.
Correct. So what we are doing, we are adding as well as we are also multiplying vector by a scalar. So any number of operations of these two types we perform, the resultant vector will also be in the vector space. That's the property of vector space. So first option should be the correct one. Next question, De Morgan's law. So I hope this is very much familiar to you from your high school as well. So what happens when you take the complement of the whole term? What happens? The individual elements get the complement as well as the sign gets reversed. So if it is a union, it becomes intersection. If it is intersection, it becomes union. So A becomes A complement, B becomes B complement, union becomes intersection. They should be correct. This should also be correct. And here, complement of A complement should be A, and then union becomes intersection, and then complement of B complement should be B. So all these options should be correct. This is the right answer. Okay, next question. Two vectors, x and y are perpendicular. If so, what is x dot y?
Dot product should be 0.
What is x dot y? Sorry.
Dot product.
Yeah, and that is xy cos theta.
Cos theta.
Correct? So let's say this is your x, and let's say this is your y. And what is theta? Theta is the angle between x and y. Now, when theta is equal to 90, what happens? Cos 90 is equal to
0.
right? When theta is equal to 90, which means x and y are perpendicular to each other, x dot y becomes 0, correct? So two vectors x and y are perpendicular to each other if their dot product is equal to 0. And if you see x transpose y, what is that? So that's just an alternate representation. What is x transpose y? So what is-
If X is a column matrix, then we transform into row matrix, and so we can multiply X and Y matrix. So that's why we take a transpose.
correct, correct. So if you have to multiply x and y, you take the transpose of the first vector. So when you do that, when you take the transpose of this one, and then you multiply it with y, what you get is x1 y1 plus x2 y2 plus x3 y2. And this is also what is your dot product, correct? This is the alternate representation of dot product as well. So x transpose y should also be equal to 0 if two vectors x and y are perpendicular to each other. Okay. Next question. For a real valued function, which of the following is true? Please note this. Real valued means whatever is the output is real. Okay. And the output is where? Is it in domain or codomain?
Codomain.
Codomain, correct? So domain is, let's say, if it is a function f of, let's say it's y is equal to f of x, then all the values belonging to x will be, all the values belonging to x will be a part of your domain. All the values belonging to y will be codomain. So for a real valued function, the output should be real, which means the y value should be real. So codomain should be R.
What about domain, madam? Domain also can be R, right?
It could be anything, right? It could be anything. You can mention that. That could be integer values, that could be real value. So, but it may be possible that these integer values are being converted to real values by the given function. That may be possible, correct?
Okay. Yeah,
So,
understood.
yeah, there's no restriction there. Okay, moving on to the next set of questions. A function is said to be continuous in R if it is continuous at least one point in R. Is it sufficient?
No.
No, it need to be continuous at all point.
All points, correct.
Yep.
Correct. Then only you can say that the function is continuous. Okay, next one. The function absolute x is continuous but not differentiable at x is equal to 0. What is, how do we visualize absolute x? Y 0.
If X is negative, then mod X is equal to minus X, and X is positive, then mod X is equal to positive X.
Correct, correct. If it is positive, it stays positive. If it is negative, you put a minus there and make it positive. So something like this. This is a function So what are we asking? Function is continuous. Yes, it is continuous. Is it differentiable? No, it is not differentiable. Here you see the rate of change of function is different here. Rate of change of function is different here, right? So it is continuous but not differentiable. So that should be true. Okay. Choose the next question. Choose the correct statement from the following. If a function is continuous, okay, we just now saw an example. If a function is continuous at a point, then it is also differentiable at that point.
No, not necessarily.
This was continuous but not differentiable. So this first option is incorrect. Next is, if a function is differentiable at a point, then it is also continuous. Isn't that true?
Yes.
It
Yes.
cannot be differentiable if it is not continuous. Correct? So this should be correct. If a function is not continuous at a point, then it is not differentiable. Is that true?
True.
Yes, true.
Yeah, something
True.
that is not continuous will never be differentiable, right? If a function is not differentiable, then it may or may not be continuous. What do you say about this?
Yes, ma'am, true.
You saw this example?
Yeah, just example.
Yeah.
Modulus x.
Yeah, function is not differentiable, but it is continuous. A function is not differentiable. It could be non-continuous, discontinuous as well. So both options could be there. So the last three choices will be correct. Next, a function fx is continuous at a point x naught if for any sequence of xi. So it's about the definition of continuity, as you can see. What does the definition say? For any sequence of xi converging to x naught, f of xi converges to x naught. So let's get back to this example. When should this be continuous? For any sequence, let's say this sequence, we are moving from left to right, following a sequence of x values. When, so this is your fx, and this is obviously your x. So when you follow a sequence of x values, the function value should converge to, so when the sequence converges to x naught, let's say this is x naught, when the sequence converges to x naught, the function value should converge to f of x naught. Right? For any sequence of xi converging to x naught, f of xi should converge to f of x naught, not x naught. First is incorrect, second is correct, third is incorrect. Okay.
Ma'am, third question, last point, can you please again, it may or may not be continuous?
Okay. Some weird example I'm taking. Is A differentiable?
No.
Is A differentiable? No. Is B differentiable?
Yeah.
Yes.
No. Overall,
There,
it
there
is
is a
not.
gap.
There is a break, right? Is C continuous?
Yes.
I'm sorry, is A continuous? Yes. Is
Yes.
B continuous?
No.
No.
So what are we asking here? If a function is not differentiable at a point, not differentiable, okay, then it may or may not be continuous. It is continuous, it is not continuous. Is this clear now?
Yeah.
It is important to mention at a point here.
At a point, very, very good. So I realized while I was speaking, so the point should be mentioned. So maybe I should have brought in this gap over here, something here, and then I would have asked about x naught. Okay. Yeah, point is important. Okay, moving on. higher order approximations are more accurate than linear approximation. What do you have to say?
True.
Right. Let me show an example. So let's say the function that we have to approximate is sine of x. Okay, and you can go for linear approximation. You can go for quadratic approximation. You can go for higher order approximations. So although linear approximations are preferred, given that they are, of course, degree 1, and they are able to provide us a decent approximation. But if you go to higher order approximations, you might get a little more, little better approximation. So the point to note here is that the approximation that you are computing for the given non-linear function, as long as you are in the vicinity of the point where you computed, for which you computed the approximation, you should be doing fine. As long as you go away from the point and try to use the equation of linear approximation, any type of approximation, as you move away from that point around which you computed the approximation, you will get a good error. Okay, so as long as you stay nearby, so you see for the sine function which we computed at x is equal to 0, this is the linear approximation. And if you, let's say, compute the value of the sine function using this linear equation, let's say at point 0, 0.2, you will get more or less the same value, the correct value. However, if you move away, let's say x is equal to 1, you see there is this gap that you get. X is equal to 2 will give you more gap, x is equal to 4 will give you even more gap. So, however, if you have a higher order approximation, this gap might be reduced, but at the cost. So let's say you increase the degree of approximation. So a is equal to 1. If you see, when you put it here, this will be a third degree approximation. Yeah, a is equal to 1 will lead to third degree approximation. And you can see that from x is equal to -1 to x is equal to 1, you are getting the precise value of the function by using this approximation. Similarly, however, if you go far away, again, you'll get an error. But if you increase the approximation degree, your estimation, your approximation gets better, right? So you see this example. Okay, getting back. Higher order approximations are more accurate than linear approximation, correct? Next, the plot of linear approximation of a function f at a point v is, can you tell me?
Tangent to f.
Yeah, it's more or less a straight line passing through that point, which is, yeah, of course, tangent to the given function. So tangent to f at the point v comma f of v. I hope this is clear. So this is the x value, this is the y value, that's all. And the point is x comma y. How do you find the length of a vector? Simple. Hope you know. Just the individual, whatever the points are. Okay, you can compute it. Very simple. Okay, next one. Which of the following?
Is there any difference between linear approximation and tangent of a line?
Linear approximation is actually the tangent. So they are same.
Means, can I say the tangent is the graphical version of this function, which what we generally use to find the linear approximation? And the same thing when I try to plot in graph, that becomes a tangent.
Yeah. So actually, I think this is explained also, I think in tutorial or in lecture also. So the equation of linear approximation indeed is the equation of the tangent passing through the point v comma f of v. So they are same. Yeah. Is that clear?
Okay.
Any doubts?
No, okay.
Okay. All right, length of vector you can compute. And next question is, which of the following vectors is perpendicular to any given vector?
0, 0, 0.
Yeah, any given vector means you bring in any vector that should be perpendicular to this vector that we will give as answer. So unless the vector is a zero vector, you might not get a 0 as the dot product. So only this should be the correct option. You bring in any vector, this vector will be perpendicular to that vector.
Ma'am, can we go to question number 1, ma'am?
One, yeah, sure.
So what I remember is that the instructor, sorry, the lecturer, he said that most of the time we will be using linear approximation.
Yeah.
But here we mentioned that higher order approximations are more accurate. But while you were explaining, you did mention the keyword that at a cost.
Yeah.
But what is the cost of that higher order approximation?
Okay. See, you could directly use the sin x function, right? Why are you approximating? Okay.
Yes.
Do you think so? Do you understand why approximations are required?
In machine learning, we require approximation to find out probability of something nearby, maybe.
Yeah. So in general, you want to simplify things, right? So let's say there is a complex model that you are, let's say in physics or any other science domain, you get some sort of an equation for some phenomena, let's say, and the model is very complex, and your aim is always to simplify the models that you produce. So that's why you prefer linear models. They're preferable. They're preferred in almost all domains. So you tend to convert any nonlinear function, let's say a function having a very high degree, let's say a function with say 20 degrees, and you tend to find a linear function that approximate the given function's behavior, however, in a given region. Okay, so wherever you are interested in finding the function's value, you should know that point. Okay, so here this linear line, linear approximation is computed at a point x is equal to 0, and you can use this equation, which is a linear equation, in order to approximate the value of sin of x. You see, sin x value you will be able to approximately tell as long as you are near x is equal to 0. Okay, and this is sometimes sufficient for us in many scenarios. But if you want more accuracy in the sense, see, your accuracy will be good in this region, but if you go far away, it will not be good. But if you want to expand your region where you want to get the approximated value of the function, you may increase the degree and you might do a little better. Well, this is a sine function where you're getting quite an increase in the region in which you can use this function. I think in tutorial there are many examples that are covered. You get very little. So I think we created a linear approximation and got some value, and then we computed quadratic approximation and got a little improvement in value. So your function has become of degree 2, which is a cost, which is again complicating your model. But the improvement that you get is very little. Okay.
And just go back to that Desmos calculus.
Yeah.
Yeah, the second equation you have written, that is the expansion series of sine, right?
Yes.
Okay.
Yeah.
Thank you, ma'am.
Yeah. Okay. Okay. Moving on to the next set of questions. Which of the following represents a multivariate function? Which one should be the correct option?
2.
RD2R.
Yeah, multivariate means there are many variables involved. So f of y is equal to f of x. What kind of function is this? This is a single variable function.
R2R.
So y is equal to f of x, let's say g. This is a multivariate function. So there could be many variables. So these variables will be sort of the domain. Okay, and this will be codomain. So RD to R. So if there are two variables, it will be R2 to R, and so on. Okay, this should be correct.
So ultimately, number of variables in the domain should be greater than the number of variables in the codomain.
No, it could be same also. Like this, the function could be of this type also. I mean, you're talking about multivariate functions.
Yeah, I'm talking about multivariate.
Yeah, in multivariate, on the left hand side, as in the inputs, should be having a number of
Greater than.
variables, multiple variables. Yeah. A hyperplane normal to a vector W with offset value B is given by. Yeah. So what is? Yeah.
One question, sorry. If R2 to R2, will it be multivariate function?
R2 to R2.
Yeah, same.
Yes. It
Number
could.
of variables.
Yes. Yes.
Yeah. Okay. Okay. Thanks.
So Mr. Input is more than what you
Yeah.
can call it.
Yeah. So yeah, correct. We are concerned about the input should be more than one. Yeah.
Yeah. Okay. Yeah.
Okay. A hyperplane normal to a vector W with offset value B is given by this. Yeah. So what is the equation of a hyperplane? W transpose X is equal to B, right? And what is W here? W is a vector normal to the hyperplane, and B is the offset from the origin. Okay. So yeah, this is the offset value B from origin. So this is good. Okay. Next question. The critical point for the function. So what are the critical points? Where the function is minimized or maximized, and how do we find them? Can anybody tell?
By
If
putting
the
first derivative is equal to 0.
Yeah. Compute the first derivative and equate it to 0, and whatever values of x you get, they are the critical points. So in this case,
0.
it will be 2x minus 1 is equal to 0. So that will be 2x minus 1 is equal to 0.
0.5.
0.5. Yeah, that should be this one. Okay, for this function, what is the critical point? Is that a maxima, minima, or a saddle point? How do we compute that?
By finding second derivative.
Correct.
Just
If the second derivative is positive, then it's
Minima.
a minima. If it is negative, then it's a maxima. If it is 0, then it's a saddle point. So in this case, it was 2x minus 1. And then you compute the next derivative, that comes out to be 2, which is positive. So it should be a minima. Okay.
Ma'am, I have a little doubt in second question. Can you please explain?
Yeah. So what is the doubt?
Can you please explain term hyperplane? How is it different from normal plane?
Yeah. So hyperplane is a general term that is used to represent multi-dimensional space. Okay. So it could be, a plane. Now this you are able to visualize because there are 2 dimensions, but there could be more dimensions which you will not be able to visualize. So in general, it could be anything, right?
Yes.
Which you would not be able to visualize. So it's a general term that is used to represent a space which is multi-dimensional. Okay.
But I think it's not linear as well.
Yeah. This is linear, correct. This is linear, correct. Yeah. So if you start from beginning, there is a line, right? There is a linear line. When you go one dimension above, you get this kind of plane, and then you can go one dimension above, then you get 3D hyperplane, and so on. You can get 4D, 5D hyperplanes. Okay.
Okay, ma'am. Thank you, ma'am.
Then you can visualize if you can, but it will be difficult. Okay, a line through point U along vector v. So what is the equation of a line that passes through point U along vector v, that is x is equal to u plus alpha v, where alpha could be any value, okay, because v is a vector and it has a direction, and you can take any value of alpha. So whatever equation of line that you get, that will pass through point u and will be along vector v. So this is the correct option. Next is gradient of a function is a vector. Is this true? What
Yeah,
is gradient?
it is partial derivative.
Yeah. So what is the difference between gradient and partial derivative? Partial derivative, so gradient is a vector of partial derivatives, right? So the whole thing, so please know the terminology. The whole vector is called gradient. So let's say you have a multivariate function f of x. F is a function of x and y. So there are two variables. So you cannot compute the derivative. What you will compute will be partial derivatives. Dou f by dou x with respect to x, and dou f by dou y, which is with respect to y. So both these things put together in the form of a vector, this becomes your gradient. Okay, and the individual elements are called partial derivatives. Okay, so gradient is a vector, that's true. Okay, next question. Contour plots of linear functions look like. Can somebody answer?
Non-uniformly spaced circle.
Okay, how?
It is equidistant space straight lines.
Equidistantly spaced. Yeah, this is correct. Okay, can somebody explain? How did you get this?
Yeah, because of linear function. Sorry, I answered space circle because of I was thinking about quadratic equations.
Okay, okay, okay. Yeah, so what is a contour plot? Okay, let's visualize some general function. Let's visualize some kind of function. Let's say this is a 3D plot. Okay, I hope you can visualize. You can visualize a glass or a bowl or something. Visualize that 3D shape, and let's say we want to plot it. We want to show how it looks like. So of course you can go for a 3D plot, but there is one option that you can make use of in plotting to represent the behavior of a 3D plot. You can make use of contour plot. Now, just to give you an idea, what you can think of is, let's say this is the function. Then you put some discs, which are cutting. They're straight like this. Visualize some discs like this. One disc, and then second disc, let's say, and then let's say the third one. Okay. Now make note of where these discs are cutting this 3D plot. Okay. And then let's say we visualize from the top. What will you look? What will you see? Are you able to visualize?
Line.
Actually, circle.
What kind of line? What kind of
Straight line. Projected
line is it?
into the x means xy
Okay,
plane.
take a glass, visualize a glass, and then let's say you cut this glass.
No, this function is just a straight line, or it will like a bowl.
It's like a bowl.
And
then I will see the circle.
Circles.
Okay. So something like this. Okay, depending on how many discs are there. Okay. So you see, this is sort of one representation of a 3D information. Okay, using contour plot. Now let's say your function is linear, something like this. Okay, and let's say again your discs are there. Okay, just imagine that kind of thing. So what kind of contour plot would be there?
Straight lines.
Straight lines. Okay. Okay, whatever you check from here, it depends on where it is cutting, right? wherever it will cut, that kind of shape. Okay. So I hope this visualization is clear to you. So there'll be equidistantly spaced straight lines. Is that clear to everyone?
Yes, ma'am.
Okay. Next question. Okay, similar to the first one. The line through this point along this vector. We saw this u plus alpha v. So u is 1 comma minus 1 here plus alpha v 1 comma 3. So this should be the correct option. Okay. Okay. Next set of questions. All right. We're given a function. Which of the following is correct? So it's just, what is the symbol? This is a grad f symbol. Okay, nabla symbol in LaTeX, you know. So grad f is the gradient of partial gradient, which is vector of partial derivatives. So what should be the partial derivatives of this function? Dou f by dou x, what will that be?
X.
3x square. That will be
3x
your,
square.
yeah. What will be dou f by dou y?
2,
Dou f by dou z will be 3.
3.
So this should be correct. Which of the following is the gradient of f of x comma y? So dou f by dou x will be
2xy.
2xy.
Yes.
Dou f by dou y will be x
X
square.
square.
Okay, this one. Which of the following statements are true? Gradient, okay, gradient of a function points to the direction of steepest ascent or descent.
Ascent.
Correct. Gradient of a function always points to the direction of steepest ascent. So second option is correct. And what would the rest? The third option. Gradient of a function at a point is parallel to the contour through the point. Or gradient of a function at a point is perpendicular to the contour through the point. So,
Perpendicular.
so you tell me. Gradient of a function at a point is always perpendicular to the contour. So second and fourth will be correct options. Okay, any doubt here? Is this clear? So, okay, you would have heard, and I also spoke about gradient descent. So gradient descent is used to get the values of parameters that minimize a function. So we compute the gradient of a function at a given point, and then we move in its negative direction. Why? Because gradient gives the direction of steepest ascent, and we need to move in the direction of steepest descent. That is why we move in the negative direction of gradient. Okay, that's the connection with the name of the algorithm as well. We move in the descent direction, which is given by the negative of gradient. This is an important thing to know. So this second option is correct. Another thing is gradient is perpendicular to the contour line. Okay, what is the rate of change of function along a contour line? What is the rate of change of function along a contour line?
It's constant.
0, right?
It's 0.
Function is constant, the rate of change is 0. Whereas rate of change of function along the direction of gradient is the maximum. Okay, so gradient of a function at a point is always perpendicular to the contour through the point. Okay, so second and fourth option should be correct. Next one, the approximation of f of x1 comma x2. So what is the equation of linear approximation? Can somebody tell if you went through the lecture videos?
It's f of a plus f dash a x minus a.
Yeah. So shall I solve it? So linear approximation is what we want, right? Linear approximation is equal to f of a plus f dash a x minus a, correct? So we are given this function which is not linear. So this is always given. You see this to be noted around this point. Okay, this is a multivariate function. So we need two values, right? F of a comma b plus dou a by dou x at a comma b into x minus a plus dou a by dou y at a comma b into x minus b. Sorry, y minus b. Yeah. So is this clear to you? Did you go through the lectures? So what you need to compute is obviously function's value at the given point. A comma b is equal to 3 comma 1 here. Okay. So dou y by dou x will be how much? So here the variables are x1 comma x2. In this equation, I've taken them to be x comma y. You can accordingly replace. So dou y by dou x or say dou x1 is equal to
2x1.
2x1. Let's say 2x. And dou y by dou y again is equal to 2y. And at 3 comma 1 is what we want. So this will become 6 and this will become 2. And function's value at 3 comma 1 will be equal to
10. 10.
10. So linear approximation, it's linear approximation is equal to f of a comma b. 10 plus dou y by dou x at a comma b. Dou y by dou x at a comma b is 6 into x minus a. What is your a? 3.
3.
Plus dou f by dou y is 2 into y minus b. That is 1. How much that comes out to be?
Minus 2.
Oh yeah, correct. Thanks. Minus 2. So 6x plus 2y. How much is this? Minus 10.
Minus 10. Yeah.
6x plus 2y minus 10. 6x plus 2y minus 10. This should be good. Okay. So I hope you know how to compute the linear approximation of a multivariate function.
I have one question here.
Yeah.
Gradient descent, is it part of univariate calculus anyway? Or what do we say it there in univariate calculus?
You can apply the gradient descent algorithm in a univariate case as well, where you would be computing the derivative. Okay. The same way, you can so you compute the derivative and then move in the negative direction of the derivative. That's all. In general, in real practice, in real world, we have many variables involved. That's why they are multivariate. But nevertheless, if you have only one variable, you can still use gradient descent the similar way.
And actually, thing is that I have not studied multivariate calculus, and I think from univariate to multivariate, it's a drastic complexity starts in multivariate. It's very difficult. I have not studied it also.
Yeah, that's nothing to worry about. So mainly, the basic thing is partial derivative is what you would need. Of course, it depends on what exactly you're trying to do in the multivariate functions case. But it's okay. I mean, there's nothing to worry. You will be able to understand that also. But yeah, in general, we do deal with multivariate functions. Because in the kind of data that we get, there are various variables that affect the target variable and the target label. So there are many variables involved, so it automatically becomes a multivariate function. But it's okay. I mean,
I need to just go through all the lectures of multivariate calculus, so that
that should be helpful. Yeah, that should be helpful. Okay. Let's move on. Okay, let's try to solve the practice assignment. It will be nice if you also are doing at your own end. Okay, let's start with the first question. We have to check whether this function is continuous or not. So what do we do to check whether a function is continuous or not? Anyway?
Check the left hand side limit, right hand side limit, and the value of the function at that point.
Correct. So we compute three things as somebody pointed out: left hand limit, right hand limit, and the function's value at that particular point. If these three values are same, then we say that the function is continuous. And there should not be any division by zero or undefined values. If they are, then the function is not continuous. So in this particular case, the function that is given is sin x divided by x. We have to check at x is equal to 0. What will be function's value at x is equal to 0? Can somebody tell?
1.
What?
X is equal to 0. What will be function's value at x is equal to 0?
Not defined, it will be right.
Not defined.
Undefined.
Not definable, 0 by 0, right?
Yeah, it is division by 0. It is undefined. So obviously this function is not continuous.
Not
But if you want
continuous.
to, yeah, but if you want to compute the left hand limit and right hand limit also, you can, then we can do that. So in that case, you can expand sin x. So the expansion of sin x would be x minus x cubed by p factorial plus x5 by 5 factorial minus and so on. Right? When you divide it by x, what do you get? You get 1 minus x squared by p factorial plus x4 minus x6 by 7 factorial. Okay. Now, if you compute left hand limit at x is equal to 0, that will be
1, 1.
right hand limit at x is equal to 0
It's
will
1.
be 1. So left hand and right hand limits are same, that is fine. However, the function's value at x is equal to 0 is undefined, division by 0. So this function is not
Once.
continuous. Okay. Is that clear?
Okay.
Let's move on. Yeah. Is there any question? Hello?
No.
Okay. Okay, all right. Next question.
I have a doubt.
So, yeah.
Sin x by x. Yeah. So if you draw the sin x by x, it looks like it is continuous.
I can't hear you properly. Can you speak a bit louder?
If we draw the graph of the sin x by x, it looks like continuous function.
If you go by the expansion, is it?
Yeah, just if we draw it on the graphing.
He's saying from the graph of the function, it is continuous.
Where did you see the graph?
No, if you plot this graph in Desmos, it seems that the function is continuous.
Can you
Because-
zoom in on x is equal to 0?
Oh.
Zoom in on x is equal to 0. Can you do that and tell me? Or
But,
move your cursor at x is equal to 0 and see what is the value of the function. It's pretty small, so you need to zoom in or maybe hover your cursor at the right point at x is equal to 0. What do you get?
Ma'am, there it shows undefined.
Correct. So it's undefined at the very point x is equal to 0, but it is fine when you move a little away towards left or towards right from x is equal to 0. Do you see that? Okay, so exactly at point x is equal to 0, it is undefined. So it's not continuous there. If you zoom in enough, you might see the graph. Okay, next question. So again on sets, this question is, we are given a universal set. You have to consider all values to be integers here. Please note that. Universal set is given, and then A is given, B is given. So these are closed intervals. Please see, they are not sets, as in they are not curly braces. They are closed intervals, which means universal set is from 10 to 100, including 10 and 100. A is from 30 to 50, including 30 and 50. Same goes for B. Can you please solve at your end and tell which one of these is the correct option?
Second is correct.
Second is correct. Is it? Okay, this is multiple choice. Okay, which other options are correct? Can you solve at your end?
Third is correct.
Third is correct. Okay. Others?
ma'am, I have just one small doubt.
Yeah.
in the earlier first question.
Yes.
Yeah, this sin x by x at x equal to 0.
Hmm.
The linear approximation says ki sin x is almost approximately at x, the value around x is almost sin x by x equal to 1.
I'm
If
sorry.
I if I take the linear approximation in that function,
Sin,
then
linear approximation of sin x divided by x.
yeah,
Okay.
then it shows ki it is 1. Approximate, not I'm saying the exact value.
Yeah,
Approx-
that is what we saw as well, right? When you expand sin x, so this is what you get. So linear approximation approximates things. Okay, and here the difference is so subtle. You see, at x is equal to 0, your function is undefined. But if you see x is equal to 0.00001, let's say, should be fine. X is equal to minus 0.0001 should be fine as well. And the linear approximation gives you approximate values. Okay. So exactly at x is equal to 0, it is not defined because we see that division by 0 is there. But if you move away from x, you should be fine. And what value you will get? You will get this. I mean, this value you get, and if you find the linear approximation, you will get this, which is what you're telling me as well. Correct?
Okay. That means the sin x sin x by x. Okay.
Okay.
What if we apply L'Hopital rule on sin x upon x? It will
That
be,
also you can do when you compute limits. Correct?
yeah, for limits. Yeah.
Yeah. For
And
limits.
then limit will be 1.
Yes, limit will be 1. Yes. Okay.
Yes, ma'am.
All right. So any other option that is correct in the second one?
Ma'am, fifth option is also correct.
1, 2, 3, 4. Fifth is correct. Okay. Any other option? What about the last option?
Last option is also correct.
Last is also correct.
Yes, ma'am.
Okay, your A complement will be
10
10
to 30.
to 29. Correct? 10 to 29.
Yeah.
Yes, 29.
And 51 to 100. B will be 10 to 49 and 91 to 100.
Yeah.
So last option A complement. A complement, okay, complement, intersection B complement. Right? So that will be 10 to 29 and 91 to 100. Yeah. 10 to 29. So you see, this is a open interval. 30 and 30 is not included. 91 is included. So that's fine. Okay. These are the correct options. Okay, next one. Which of the above terms are equivalent? I think we discussed this a while ago. X transpose Y, X dot Y are
Ma'am,
same.
all are
All three
equivalent.
same.
1 and
what
2.
is this? Yeah, 1, 2, 3.
One,
All
two,
are correct. Yeah, this should be correct. Linear approximation of tan x around x is equal to 0. So note this, you are given around which point you want the approximation. You can never be asking an open-ended question because, as I said, linear approximation is always around a given point. So tan x, so what is the equation of linear approximation? F of L is equal to f of a plus f dash a
Yes.
x minus a, right? So all that you need is the derivative and put the right values. So derivative of tan x is equal to secant square x, okay? And tan 0 is equal to 0 and secant 0 is equal to 1. Can you put in the values and tell me the equation of the linear approximation? Yeah, we need the equation.
1 plus
X.
We are getting x. Okay.
x.
All right. Good. So this will be your linear approximation of tan x around x equal to 0. So you see this complicated function is now converted to such a simple linear function, that to such a simple one, as long as we are near 0. So you can use x is equal to, you can use you can use this function to compute this function's value, let's say at 0.05. Okay, 0.05 is near this 0. So it's so complicated to find tan 0.05. Let's say you don't have calculator, right? And here you're able to manage with this function, approximative function. That's the advantage.
Ma'am.
Yeah.
Ma'am, if a function is not defined at a certain point, then can any higher order approximation be defined at that point?
No, that's not. At that point, no.
Okay.
See, so what I can think of is, let's say this is the non-continuous function. Let's say you are computing the approximation at this point, okay, and then to compute the approximated value of the function at this point, you are using that linear approximation. You will get some value, correct? But that may not be the right one, right? That may not be the representative of the actual function. This is your actual function f, and you have got a linear approximation of this f at this point, and you are making use of that equation to find function's value at this point. Of course, you will get some value, but then that may not be right. Do you understand that?
Yes, yes.
The function is undefined means definitely the function get discontinued at that point.
Yes.
Can I say that?
You can say that. Yes.
Okay.
Okay, partial derivative of this with respect to x, what will that be? Partial derivative with respect to x will be 3x square, and
3.
x will be 3.
3.
Okay. Is this function continuous?
Yes,
Sorry.
ma'am.
Yeah. So to check.
Yes.
To check for continuity, you check left hand limit, right hand limit, and the function's value. Function's value at x is equal to 1 is how much?
9.
Function's left hand limit is
9.
Right hand limit is, so for right hand
9.
limit you will use this thing, right? The upper one. So at x is equal to 1, that will become 9. So all the values are same. So it is. Which of the following is the best approximation for this? Now you see e to the power 0.019. So complicated, right? Assuming you don't have calculator. What you can quickly do is compute the linear approximation of which function? E to the
X.
x, correct. And what x value you should take? What a value you should take? As in around which point you should compute the approximation?
0.19.
0.019.
019.
0.
0.
See,
Oh, 0, 0. Right. Yeah.
You are interested in using that approximated equation to find the function's value at 0.019, which is in the vicinity of 0. So it suffices to compute the linear approximation of e to the x at x is equal to 0, and you should get a value which is close to the actual value. Now, isn't this quite simplified?
1.
Yeah. So what are you getting?
1.
Okay, let's see. F of x is e to the x. A we will be taking to be 0. So linear approximation we have to find. So that is f of a plus f dash a into x minus a. F dash x is equal to how much?
X into A.
Sorry? Yeah, f dash x is equal to e to the x itself. So at x is equal to 0, it will be 1. At x is equal to 0, it will be 1. So our linear approximation becomes f of a 1 plus f dash a 1 x minus a 1 plus x. Did you get this? Now we want L at 0.019. That is, instead of x, we would put 0.019. So we get 1.1.01. This should be correct. Any doubts so far? Okay. Let's move on. What is the linear approximation of this function? Okay, can you compute this? You know the equations we just now did. There are two variables here, so we use partial derivative.
Plus 2y. The second one, 2x plus 2y minus 2.
Very good, that was quick. Did others get it as well? Do you want me to solve it?
No.
No, ma'am.
Okay. Okay. What is the gradient of f of xy is equal to x per y at 1, 3? So dou f by dou x will be 2xy and dou f by dou y will be x square, right?
6,1.
2xy will be 6, yeah. Y square will be, no, not y square, x square. That is 1, yeah. 6,1. Okay. What are directional derivatives? Did you go through the lectures?
Last two parts.
Vector divided by its absolute value.
Not completely. So directional derivatives are weighted sum of this should suffice. Weighted sum of partial derivatives. Now, what is this weighted sum? We'll talk about it. Partial derivatives, you know. So let's say there is a function that is given and you have to compute its directional derivative at a given point. Of course, that point will be given. Since it's a directional derivative, a direction will also be given. A direction will also be given. Okay. In that direction, we have to compute rate of change of this function f at a given point. Okay. So it's a weighted sum of partial derivatives. So first you will compute the partial derivative of f, which is grad f. Now weighted sum. This weighted sum will be computed as per this direction vector. Let's call it d. So always the direction will be given to you. First, what you have to do is you have to convert that direction vector to a unit vector, u. You know how to do that?
Divide by norm.
Yeah. Let's say this is a vector. You have to convert it into unit vector. So you divide by
root 5.
Yeah. So you get this becomes your u. It's a unit vector. That means the magnitude of this will be 1. So this is what you need to get the direction, and that the individual components will be used to get the weighted sum. So how do you get the weighted sum of partial derivatives? So you'll write directional derivatives is equal to first component multiplied by dou f by dou x plus second component multiplied by dou f by dou y. Now you might also be given this point, let's say a comma b. You have to find the directional derivative at a given point. So that point you will put here. Okay, this is how you compute the rate of change of function in a given direction. Okay, so directional, gradient, which is the vector of partial derivatives, that tells you the rate of change of the function, where that gives you the direction where the rate of change is maximum. Okay, but sometimes you are interested in a different direction where the function might not change the maximum. So that's a customized requirement. You want to see how much the function is changing in a different direction, in a given direction. So that's where directional derivatives are required. Okay, so what are we asked here? Directional derivative of this function at this point along the unit vector. Sometimes you might be given a unit vector, sometimes not. So you can check that. You always need a unit vector to get the weighted sum. So let's see. The gradient will be 2x, yeah, 2x, and then 3, and then 2z. That is your gradient. Now at 1 to 1, you need it at 1 to 1. Okay, that will be 2. This was 3, right? 3, and this is 2, correct? Yeah, 2 to 1. And now let's see the direction 1 minus 2, 1. 1 minus 2, 1. This is not a unit vector. So we divide it by 1. That is square root of 6. This is your direction vector, that is unit vector. Okay, this is correct. Now your directional derivative at this point in this direction will be weighted sum of partial derivative. So what we'll do is, what have we asked? Yeah, with the value they're asking. Okay, so whatever that comes out to be, that should be your value. Is this clear? I hope that is clear.
Yeah. Yes, ma'am.
Okay. Next, so find the direction of steepest ascent. So you see here, they're not directly telling what is to be done. We need to find the direction of steepest descent. The direction is not given. Function is this, point is this. Sorry. So we are not given the direction. So I told you which is the direction of steepest ascent.
Gradient.
Gradient. Okay. Can you do it at your end right now, just the way I did it? Let's see what you get. You can ask me if there is any doubt. 1, 3, 4. So they're asking only the direction, you see, not the directional derivative. Please note, it's even simpler.
The first one, ma'am.
Yeah, looks like, yeah, the correct option is first. That's good. Is everybody done it? So what we do is we just compute the partial derivatives and we put these values in place of x, y, and z. And since they are asking for direction, it's a good idea to find the unit vector. So this should be the correct one. I hope that is clear. Okay, next one. The directional derivative of this at point this along the unit vector is, yeah. So here you have to compute the uh, weighted sum of partial derivatives. Can you do that? Or let me know if I should. Okay, let me do it. If it will take me time. Simple. It's 1, 1, 1, and then unit vector we want 1 minus 1, 1. That will be okay. Right. So directional derivative will be simple, right? Yeah, that's all. 1 by square root 3, whatever that comes out to be, that will be the answer. Okay, you can just compute that. Is it clear? Any doubts?
No.
Okay. All right. Okay, which of the following are the vector equation of a line that passes through this and this? What is the vector equation of a line that passes through a point, let's say A, and goes through a vector u? Okay, this is the equation, right? So here we are given 2 points, A and B, let's say, let's call them A and B. Now, if you want to convert into a similar fashion, so this is A, let's say this is B, the line passes through these points, which means this can be taken as a point A, and we need U, right? That's the direction. So this is the direction. This could be the direction. This could be the direction. So it can become A plus alpha B minus A. B minus A gives you the direction. Can you hear me? There's a power cut here. Hello, am I audible?
Yes, yes.
Okay. Okay, please let me know if there's an issue. Okay, this is one option of the equation. The other could be the other way around. We can see the line passes through point B and it's in the direction A minus B. Both will be the correct equations of the line. So here in this case, your A is 1, 2, 3, B is 4, 0, 1. So 1, 2, 3 it passes through, and then the direction will be B minus A. 4 minus 1, 3 minus 2. Yeah, first one should be correct. Okay. Second option, it passes through point B, which is 4, 0, 1 plus alpha. For the direction, you will take A minus B, which is 1 minus 4 minus 3, 2 minus 0, 0, 3 minus 1, 2. So second option is also correct. This should be the correct option. Okay. Okay. Next, Cauchy-Schwarz inequality. What does that tell you? Anybody?
No, this one, ma'am, forward. Please explain.
Okay, Cauchy-Schwarz, in case of vectors, what this inequality tells you is that given any two vectors, their dot product will always be less than equal to the multiplication of their magnitudes. Okay, so what it tells is, let's say you have two vectors A and B, then their dot product let's say they are very complicated, huge vectors, and you don't know, you have no idea about their dot product and you have not computed. But one thing that you can say for sure, without even looking at what the values there are, A dot B dot product will always be less than equal to magnitude of A multiplied by magnitude of. So this is the inequality that is given by Cauchy-Schwarz. Also, so in which case will it be equal? Let's talk about that. So A dot B will be equal to A multiplication of both magnitudes when A is a, okay, let's say alpha. A is a scalar multiple of B. Only in that case, these will be equal. Okay, either A should be a scalar multiple of B or B should be a scalar multiple of A. In either of these two cases, the dot
Since A and B are in same line.
Yes, correct. Correct.
The vector is in same line.
Yes.
Okay.
Right. So, in such a case, the dot product will be equal to multiplication of the magnitudes. And another thing is when A is equal to minus alpha B or B is equal to minus alpha A, they are in the opposite direction. Okay, in the same line but in the opposite direction. In that case, your A dot B will be equal to minus of A magnitude multiplied by magnitude of B. Okay, so this thing. Now, what are we asking the question? As per this inequality, if B is a negative scalar, yeah, B is equal to minus alpha A. Then, what did we say? A transpose B or A dot B will be equal to negative of, negative of multiplication of A and B magnitude. Yeah, this should be the correct option. Okay, I hope that was clear. Any doubts in what have we discussed?
Right. The norm, right?
Hello? Sorry, I couldn't hear you.
Like by magnitude, you mean the norm of the vector,
Yeah,
right?
yeah, correct. Yeah, so what have we just computed? This thing. This is the magnitude, right? It's vector. This is the magnitude. Did you all go through the videos or you're yet to see them? Just I'm out of curiosity, I'm asking. Today is Monday, so it might be possible that you have not seen.
Ma'am,
And
last one is remaining because this session is too early.
last video is remaining to be watched, is what you meant?
Yes, ma'am.
Okay. Yeah, this session is a little early, I understand. So next one will be late, I think. By then you all would have watched. But just like that, I wanted to know from you how many people have watched the videos, because it's a good idea to have watched the videos, of course, before any session takes place, so that you can join in well, right? You can make full use of the session. Anyway.
Multivariate is missing for me.
Okay, all right. Good to know that you people are watching whenever possible. So in the next session, we will solve some questions. So that will be nice. I think by then you all would have watched. So that will be good interactive. Most of the people would be talking. Right now, only there's a power law, kind of power law. Only very few people are, interactive. The rest are the audience teams. Anyway, any doubts in whatever we discussed?
No, ma'am, not yet.
But if you discuss the hyperplane part, then it will be good for us. Means if you can demonstrate that hyperplane concept in GeoGebra.
Hyperplane is discussed in lectures or not? Okay, can you correct me? It's been some time when I saw it.
Actually, I haven't seen that multivariate part.
Okay, you do one thing, you take a look at the lecture videos first, and if there is any doubt, we can take that up in the next session. Or maybe what I'll do is I'll try to add some question also on that. I'll try that for the next session. Will that be fine?
Okay.
Yeah, let's do that. So you watch the lecture videos first, because it's something that has already been prepared. First go through that. If there is any doubt, then we can take that up. Okay. All right.
One question I have, ma'am.
Yeah.
You will be one instructor for us, and one more person was there in the last call, Ram.
Mm-hmm.
So only 2 people will be there.
So there'll be more people actually. So in different weeks, you might get different people.
Okay.
So last week 1, second session might be Vishal, right? Somebody else might be there in second session, or both sessions were taken by Ram?
I attended the second session only.
Okay. Okay. Anyway, there'll be more people coming in for different weeks. Yeah.
Okay. That's good, because last session was not good for us actually. We were stuck with linear equation involving x squared term.
Oh, is it?
So yes.
So you had doubts there, is it?
Yes. So
What
maybe
you can do is, if you still have doubts, you can post the question on discourse. I think that should be helpful, so that it can be answered at a decent pace.
okay. Yes, I'll do that. Thank you,
Yeah.
ma'am.
So to answer your question, there'll be different people in different weeks. Yeah.
That's good. Good. Thank you.
Okay. All right. So looks like there are no more questions, but I see good number of participants, which is good. I hope they were listening as well. It was a good session. Thanks all for joining in, and we'll see you in the next session with some questions, and we'll solve along.
Thank you, ma'am.
Thank you.
Bye everyone.
Thank you,
Thank you, ma'am. Bye.
Great session. Thank you.
Yeah, thanks. Same here.
Thank you, ma'am.
Thank you, ma'am.
Thank you.